Okay, welcome to another exciting video brought to you by Upvision Concept Academy. This time around, we're going to be looking at the first and basic topic in physics, units and measurements. Now, this series of videos in physics is tailored towards those preparing for WAEC, GCE, JAMB, NECO exams, and every other related exams. So whether you are studying for these exams or you are just interested in having knowledge of physics, this video is for you. So we'll start with measurement, and we say that measurement is the means of communication in sciences by scientists. For instance, if a scientist want to communicate a shape to you by describing, it will just give you the dimensions of that shape. So you have this shape as a rectangle, basic shape as a rectangle. We all know rectangle. But for a scientist to communicate to you what kind of size or what size is this rectangle, it will give you the dimensions. It will just say length, for instance, 6 cm, breadth, it will give you 4 cm. So even if it doesn't draw this for you and it gives you the dimension that has been measured, you can go and reproduce the image by looking at the scale of this. So measurements are actually a means of communication in science. Now we have two quantities. We have the fundamental quantities, and the derived quantities. Okay, so the fundamental quantities are actually the quantities that are independent. They are just not gotten from any other means. They are just the basic quantities in physics. You see an example of a fundamental quantity like length. You understand? It's not gotten from anywhere. Length is length. Time is fundamental quantity. Another example, mass is fundamental quantity. And you have things like electric current. Electric current is fundamental quantity. You have temperature. Temperature is fundamental quantity. What else again? Amount of substance, which is like mole, is fundamental. Amount of substance. So these are fundamental quantities. So, like as I said, they are not derived from any other. They are just standing alone. Understand? They are not derived from another quantity. Now, a derived quantity could be something like force. It could be energy. Energy is another quantity that is derived. You can have work, rate of work done. Sorry, work is force times distance. Energy is rate of work done. Okay, power is also from a derived quantity. What else? I have momentum. We'll look at all this, pressure, and so on. We'll look about the units. For length, unit of length is in meter. You have meter, and so on. You have time. Time is in seconds. Meter is just one of the dimensions. You can have it as centimeter and so on. But these are the basic thing. So this one now is seconds. That's the units. Let me just put it under it. This one is kilogram. These are actually called the SI units. They are called the SI units. But before now, they call them the MKS. M is meter, K is mass, and S is seconds. But they call the SI units. So when you see the term SI units, that is System International. You are talking about these fundamental quantities. SI unit is System International. It's a French It's a French, you understand, international. So you have it as that. Electric current is in ampere, temperature is in Kelvin, and this one is in moles, amount of substance. So the difference, derived quantities are gotten from the combination of fundamental quantities. So if I come here and say force, force is mass times acceleration. See that mass is already this fundamental, and acceleration is gotten from here because acceleration is a combination of distance and time. And distance and time. You see, let me come here. Force is equals to ma, right? And m times a is the change in velocity and the change in time. What is velocity? Velocity is actually distance per time. You understand? So distance is length, is already here, and time. So everything will go into dimensions while we are talking about this. But I'm trying to just tell you that derived quantities at this point, derived quantities is gotten from the fundamental quantities. No matter how you look at energy now, energy is what? The rate of work done. Work done is what? Force times distance over time. This is energy. Energy. Force again is mass times acceleration. And we have come here and said this one is already coming from here. Distance is length coming from here. Time is coming from everything coming from here. No matter how you dissect these formulas, you understand, you will still see that they are derived from fundamentally these fundamental quantities. All right. Okay. So we'll look at measurements again in details and see how different quantities are being measured. Different quantities are being measured, like length, like volume, like okay, I'll start with length. So instrument for measuring length, for instance, these are the quantities, length. So instrument for measuring length, instrument for measuring length, for measuring length includes number one, we have the meter rule, ruler, meter rule. You know how it's calibrated now? It's calibrated. So the accuracy for meter rule, accuracy is 0.1 cm. That's the accuracy, 0.1 cm. So what's the meaning of accuracy? It means that this is where the lowest this thing will stop. I cannot measure 0.125, which is meter rule, cm. It's only calibrated in cm, and the cm is I can measure, for instance, 1, 2, 3, or 3.5, 3.6, and so on. I cannot be measuring 3.625 because my accuracy is not, I don't have it in this other units. It's only 0.1. So it's only 0.1 between 0.1 to 0.9, then it graduates to 1. You understand? Anything that is having some intense decimals, you will not be able to see it in the meter rule. So that is it. So the meter rule is the basic instrument for measuring length in physics, in sciences. Okay. So again, what else? We have the vernier caliper. The vernier caliper is another measuring instrument. Vernier caliper. Okay. Okay. So you will see how it is in textbooks. You can research on it. Vernier caliper, the accuracy is 0.01 cm or 0.1 millimeter. So please also know how to convert these dimensions. 10 millimeter make 1 centimeter, 10 centimeter make 1 decimeter, 10 decimeter make 1 meter. From cm to meter is 100 cm make 1 meter, and so on. Learn how to do this conversion while you are studying physics. Okay, so this is the vernier caliper. Then, as we go further, we have the micro screw gauge. The micro screw gauge. This one has high accuracy. The accuracy for this one is 0.001 cm. This one is very good for measuring small things. The other thing you need to know is to convert standard form. If I want to express it as a standard form, how do I do it? This accuracy here, let me do it standard form. 0.001 in standard form is equals to, I just move my decimal point here, 1, 2, and 3. It must come to where this point is. So I put 1 here. Because I've moved it, then times. Because I'm moving from left to right, the power is minus. So 1, 2, and 3 minus 3. You understand? cm. This is how this is expressed in cm. This is how it's expressed in cm. So you see how we use standard form in physics. Please note, if you are going from left to right, 1, 2, 3, it's minus. If it's from that way, let's say for instance, I want to do 1000 in standard form. This is where the point is. I go 1, 2, 3. So it's equals to 1 times 10 to the power 3. Positive 3 because I'm going from what? Right to left. Right to left is positive power. Left to right is negative power. Okay. So that's for micro screw gauge. Another instrument for measuring length. Okay, so the one that has high accuracy is micro screw gauge. If you're asking in JAM, which of the following measuring instruments has the highest accuracy? Highest accuracy is this one. This one, it's more precise than this one. Though you can use it for different things. This one now, if you don't care about some kind of accuracy, you can use this one. You understand the meter rule. But if you really want to measure something very, very small and want to get it to this decimal point, micro screw gauge is your best bet. So we've talked about length. The next one we'll talk about is measurement of volume. Measurement of volume. So for volume, you have different things you are measuring. Rectangular block is rectangular block. So by the time you measure all the sides, to get it, it's just length times breadth times height, LBH, and the unit is in meter per meter cube. So rectangular block volume is length times breadth times height. Okay. So for sphere, what's a sphere? Okay. No, this is for rectangular. For irregular solid, this one is regular. Irregular solid. Now, mind you, you have to combine mathematical skills to get all this. I'm just using rectangular block for the generic description for regular shapes. Understand? There are some times where you might need to get that of a frustum, of a cone, of different things, of different shapes that are regular, that have defined formulas. But for irregular solids, how do we measure the irregular solid? We do so by immersing this irregular solid inside a liquid that will not dissolve it. You will immerse this irregular solid inside a liquid that will not dissolve it. And the displacement, that volume that is displaced, is what you will now measure and equate it to the irregular solid volume. What's an irregular solid? Irregular solids are solids that are shapeless, things like this. I don't have a formula for something like this. If it is a 3D solid, I don't have a formula for something like this. But if I want to measure it in the lab, I can put a measuring cylinder here and put a liquid inside this measuring cylinder. Of course, this thing should be able to enter. I put a liquid. This cylinder is calibrated. This calibration. Calibrated. It's calibrated. So there's a liquid inside here. First of all, before I put this one inside, I'll tie a rope like this. Before I put it inside, I would have marked where this liquid is. But by the time I immerse this inside here, this volume of this liquid will also rise. This liquid will also rise. Why? Because as this one enters, it displaces it. It occupies a space inside this liquid, and those other liquid will go up. So the new volume, this is volume 1 and volume 2. The difference volume 2 minus 1 will give me the exact volume of this irregular shape, irregular solid. So this is like a Archimedes principle or upthrust. We'll do that later. And you see that you can also use a is it cylindrical can they call it now? That's a can that has an outlet like this. So if I put my liquid up to this point, this is a can, and there's an outlet for it. So that anything I put inside here, you understand, this liquid will be displaced into another can. You understand? So if I put this regular solid inside like this, the water, the solution, the liquid will now come out. Whatever comes out here is equal to what? The weight of this thing, or the volume of this thing. So the volume of liquid displaced, that's what they call it. The volume of liquid displaced by this one is the volume of that particular shape, that particular solid. And the condition is that I'm not going to put this thing inside a liquid that will melt it or that would dissolve it. Please, that's the word, dissolve it. As long as this liquid is insoluble, it's not soluble. It does not dissolve this guy. So I can do that. So that's how you measure irregular shapes. Then for things like sphere, we're talking about volume. For sphere, I can see my board. Sphere, there's a formula for it. So sphere is 4/3 pi r cube to get the volume of a sphere. Okay, then cylindrical wire also has a volume. The volume of cylindrical wire. Okay, let me remove this one so that I can share with you volume of a cylindrical wire. So the volume, cylindrical wire. So the volume of cylindrical wire is pi r square L. Pi r square L. So that's the volume. Or this pi is this pi r square. This r is d. You understand? D over 2. So pi instead of having r, I have d over 2 all square then L. So it's the same thing as saying pi d square over 4L. So this is also volume expressed in terms of diameter. Okay, so I've seen that. I've seen the volume of liquids. So for liquids, we have seen cylinder. We are measuring of volume. We have talked about rectangular block, irregular solids, sphere, cylindrical wire. Now we'll talk about liquids. Liquids simply use pipettes or burettes. In the chemistry lab, you see that very well. Pipette or burette is what we use in measuring the volume of liquids. So that one is simple enough. Then let's go to the next one, mass and weight. What is the difference between mass and weight? Mass is the quantity of matter or material in a substance, while weight is the attraction, the pull of that matter towards the ground, towards the earth. So mass is defined. Mass is the quantity of matter in a material. While weight is the force or pull, is the force or pull of what? Or the force or pull with which the earth attracts the material. So a force. So why this one, weight is measured in newtons, mass is measured in kilograms. Why weight is measured in newtons, mass is measured in kilogram. Okay, so for mass, we use beam balance to measure mass. Beam balance is an equipment used to measure mass. And the weight is found by using a spring balance. The spring balance is calibrated using Hooke's law, which states that the extension of a spring of the balance is proportional to the applied force as long as the elastic limit is not exceeded. We're going to be looking at Hooke's law later on in this course, in this physics class. So mass is measured in kilogram and weight, the unit is in Newton. Understand? This is kilogram, and the instrument is the beam balance. The beam balance. That's what we use in measuring the mass. While the weight is what we use the spring, the spring, the spring, the spring, and the spring balance. Spring balance. They are both balanced. One is spring, one is beam. Okay. They are both balanced. One is spring, one is beam. Okay. So we'll look at dimensions of physical quantities. Dimensions of physical quantities quickly. Dimensions of physical quantities. This one, you see it in JAM often. So fundamental quantities, length is represented by L. That is if you want to use dimensions to do it. And then mass, M, is M, big M. Then time is T, big T. Remember I said that all these are fundamental quantities. So it is, in dimension, we try to use fundamental quantities, mass, length, and time, to express anything that you are given. So if, for instance, they say we should find dimension of length, of velocity. So you start by defining it with the formula. What is the formula for velocity? Velocity is what? The change in length, change in distance. Let me use it this way. Change in distance. Change in distance over change in time. Now, if distance change, you know that it is from maybe L1 to L2. And distance is just length. It's just length over time. And with dimension here, L over T is already velocity. So therefore, velocity in dimension, velocity as dimension is L over T, or express it in terms of one linear form, LT raised to the power minus 1. So this is the dimension for velocity. So in dimension, you must have your formula, whatever quantity you are given, broken down in terms of L, M, and T, no matter what. Let's do another one. If, for instance, they say you should find dimension, get the dimension for area. What's area in definition? Area is what? Length times breadth. You have been knowing that length and breadth is length. So length is squared. As length and breadth. Breadth is the other way of saying length. That's distance. So L squared. So this is dimension for area. Volume, the same thing. Dimension for volume is L cubed, because it's the 3 sides you are multiplying. Understand? If, for instance, they say you find the dimension for force. Okay, it's getting hotter. For force, what is force? What is force? Force is what? Mass times acceleration. Already, M is already there. So I will leave this M and focus on A. A is what? Change in velocity over time. Change in velocity over time. Is it not? Now, this velocity is what? Change in length over time times 1 over t. See, this one is the velocity and this one is this time. You understand? If A is equals to, that's acceleration, please. If A is equals to v minus u over t, is the same thing as saying v minus u times 1 over t. Meanwhile, this change in velocity v is the same thing as L over t times 1 over t. So L over t squared is the same thing as saying L t raised to the power minus half. So this is the dimension for acceleration A. Now, if it is a pressure we're looking at, pressure, let me erase it. Okay. So if we're looking for pressure, what is pressure? Pressure is force over area, force per unit area. So pressure P is equals to force over area. Now we already know that area A is what? L squared by dimension. And force is MA. You understand? M is already a fundamental quantity. For acceleration, we have derived acceleration as what? A is equals to LT raised to the power minus 2. Remember? Okay, let me derive it again so that you don't forget. Acceleration is what? Change in velocity over time. Remember, change in velocity over 1 times 1 over time. Change in velocity, remember, is L over t times 1 over t. This one is simply as saying L t raised to the power 2. That's how I have it here. So I have this, I can put it here. Pressure is equals to, where I see force, I put MA. Instead of putting A there, I put LT minus 2. You get it? LT minus 2. That's for MA over L square. So pressure is the same thing as saying M dot this L dot this L is L minus 2 and T minus 2. Raised to the power minus 2. These two can be resolved. You understand? This raised to the power 1 to the power 1. So pressure is equals to M. So these two, I take one of it and add the power, which is 1 plus minus 2 minus 1, then T raised to the power minus 2. So this is the dimension for pressure. Dimension expressed only in terms of MLT. I must not see anything other than these three things in dimension. I must not see anything other than these three things in the dimension. Dimension is breaking down whatever derived quantities into these fundamental quantities. That is for that. Okay. So I've done pressure. We can play with force. We can play with work. What's work? Work is force times distance, right? Okay, I'm taking up at least you know the fundamental now. MLT, 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 MLT. Okay, so that's the fundamental quantities. So for work is the force times distance. Force is what? Mass times acceleration times distance. Distance is L. Mass is there. So acceleration is what? M L t raised to the power 2 times L. So work is M. L and L is L squared, then t raised to the power minus 2. So this is dimension for work. Okay. Now there's this question that normally comes out in JAM. It says, let me put it on the board and do it. Wrap up the class with that question. It comes out in JAM, but it's about dimension. They say it in different form, but I'm going to put it the way it is in the material I used in preparing this lesson. So it says, for example, we are going to be proving that. Okay, let me say consider the formula. Velocity. Final velocity equals to initial velocity plus AT. So verify whether this is dimensionally correct. Whether this side is equal to, I can see the dimension here. What I'm seeing here is the same I'm seeing here and here. I should verify. First of all, velocity, either initial or final, is changing length over what? Time. Velocity is changing. So even u is equal to what? L over t, which is equal to L t minus 1. And v to the same thing, v to the same thing, L over t. Okay, let me just write v. A is what? A is what? L over t squared. That's A. Or L t minus 2. That's for minus 2. Now, for this one, where I see v, I put L t minus 1. This is v. Then this is another v again, L t minus 1. Abi? Plus A. A is what? L t minus 2 times t again. That's this t. And this is raised to power 1. So if I say LT minus 1 for, this is for V, and LT minus 1 for U, plus this one I have to resolve it. There are half t here, half t here. This one half power of 1, this one half power of 2. So L, take 1t, add the power. If you add minus 2 plus 1, you still get 1. Sorry, you get minus 1. So if you check this, inspect this equation, you see that I have a dimension here that is also this first term and also this. That means this is dimensionally correct. It's correct because every term is the same. Every term in the equation is the same. It's having the same quantity L, the same quantity t raised to power minus 1 throughout. So the equation is correct dimensionally. That's what that means. Normally comes out in JAM. So I'm going to stop here for today. Please subscribe to our channel to get more exciting physics videos, chemistry videos, math videos. I really hope this is informative for you. I'd like to thank you for viewing.